What is correlation? Let's try to understand this a bit more in detail. Remember, one very important idea that we covered was whenever you're trying to do machine learning to predict some output, you need to choose what input features you want to take, right? You want to choose what are the inputs which are good predictors of the output. That part is very, very important. We have to put a lot of focus to choose which are the inputs which are good predictors of the output. Isn't it? Imagine there was a salary prediction model that we were discussing to start our, like we were talking about that model to start with. And we discussed that to predict the salary of a person, what are the most important predictors of salary? So if you want to predict the salary of a person, what are the most important predictors that are used to predict the salary? What are the most important predictors? Because if you can choose those predictors or inputs well, then you will get an accurate prediction. Okay, so it's very important to choose those inputs or predictors properly. If you can choose those inputs or predictors properly, and if you can choose inputs which are good predictors, then your outputs will be more accurate. Imagine if you are trying to do sales prediction. Here we are doing sales prediction. So these are relevant inputs, right? I mean, so the sales of a company indeed depends on their advertising expenses. So if you're spending more on a particular TV platform for advertising money, if you're advertising more, you will get more sales. You will get more visibility amongst your prospective customers, and people will know about your products and they will buy your products. So sales will inherently go up, right? Is expected. But what doesn't make sense is if you want to predict your sales, you will not want to predict your sales based on um, the average age of your company. Doesn't make sense, right? So the age of the company has nothing to do with sales, right? I mean, we can argue that okay, if the company is older means I mean to say the like how when it was established. I mean, a company can be established 20 years back. A company can be established yesterday, but the sales is not a direct, factor of that. There are a lot of companies which were established uh, 50, 70 years back as small family businesses, and they are doing no sales at all. They've all shut down, let's say. But imagine there was a company that was established just yesterday, a very new startup company, and they are doing brilliant sales. So the sales doesn't depend too much on the family history, the establishment history, but sales is ultimately a function of how much you're able to make your consumers aware about your product. Are you advertising more? Are you having a good quality product? It depends on those fundamentals. How strong a team do you currently have? So the current indicators matter, not something you did 70 years back matters. Of course, there are established businesses which are outliers, but generally, what I'm getting at is the output. Whenever you're framing any data science problem, it is very important to identify what inputs are predictors of the output. You will not want to consider some input X, which is a bad predictor of the output Y. And that is where the correlation matrix gives you a very good understanding. And this is again a very theoretical topic. If you remember, we were looking up Gemini. Gemini did give us something called Pearson's correlation and all that. So it's a fairly theoretical topic, but the core idea is uh, correlation typically ranges from -1 to +1. If you look at Pearson's correlation coefficient, it typically ranges from -1 to +1. So this is the range of Pearson's coefficient. -1 to +1 is the range. And the most important factor is the magnitude. We look at the magnitude of the correlation. How strong is the correlation? There are two aspects. One is direction, one is magnitude. Direction will tell me, is it positive, is it negative? +1 means positive correlation, -1 means negative correlation. That is how we understand the direction of the correlation. What is the direction of the correlation? Magnitude of the correlation tells us how strong is the correlation. Is it a strong correlation? Is it a weak correlation? So what is important for us is to understand the strength of the correlation, not so much the direction. And you can clearly see that between sales and TV has a very strong correlation with sales, 0.78. Actually, TV has the highest correlation with sales, which means that if I know that I'm spending more on TV, definitely I will get more sales. So you can use this as an indicator to understand which are good quality features. Even similarly, the next best feature is radio, and the next best feature is newspaper. Newspaper is actually a very poor quality feature because correlation zero means it's a very bad correlation. Positive is positive correlation. One is more, the other X is more, Y is more. Negative is negative correlation. If X is more, Y is less. And zero is zero correlation. There's no relationship, right? That's the idea. And if you want to get a little deeper into this topic, maybe it is justified to talk because it's a bit of an important topic also. I can take you to my notes and just give you a slightly deeper understanding of correlation. Yeah, I think this diagram will clarify everything about correlation. See, look at this one, all of you. We have two variables. We have ice cream sales and temperature, and we are studying the relationship between ice cream sales and temperature. So we are looking at day-wise data. Each and every day, we are tracking what is the temperature of the day and how much of ice cream sales we are making on that particular day. And we can clearly see when we go and plot this data, we can clearly see that more the temperature, typically more the temperature, more the ice cream sales. This is what we refer to as positive correlation. If the X is more, the Y is also more. If the temperature is increasing, the sales is also increasing. So similarly, we can look at the next one, which is temperature versus jacket sales. So as the temperature increases, the jacket sales decreases. This is what we refer to as negative correlation. This is minus VE correlation, negative, inverse. So as the days get hotter, people buy less jackets. We are seeing a kind of a downward spiral. Similarly, we are seeing two more examples. You can see income versus spending. Income versus spending is a positive correlation because typically more the income, more the spending on an average. There can be some outliers. There are people who are earning more, but they are spending even lesser. Maybe at a point in time in life when you tend to earn more, you also tend to save much more. So your corresponding income actually reduces a lot more. That is also possible. So, and another very interesting thing that is happening here is if you see, uh, if your income increases, spending increases on an average, but it's a lot more spread out. It's not the same strong relationship we saw here. The relationship is not that strong as we saw here, but it's more spread out, it's weaker. And the same applies here, health age versus health quality. You can see that as the age increases, the health quality reduces. Again, it's a weaker correlation. So as we see these examples, how are we measuring correlation coefficient? We are measuring this using something called Pearson's correlation coefficient. Now, this is the part where I was mentioning that, in bits and pieces, we will end up coming across some jargon, some theory, but don't worry, right? So these are some mathematical parts which you don't need to worry about, but understand the concept behind it. That's most important. So we use something called Pearson's correlation coefficient, which is given by small r. And the Pearson's correlation coefficient is usually ranging from -1 to +1. And there are two aspects to the Pearson's correlation coefficient. Now, these are the numbers I've generally given. Don't worry how I'm getting these numbers. These are only random numbers I've given, 0.9, 0.4, 0.3, but there are ways to calculate it. But here in this example, I've just randomly given the numbers. And whenever you look at any particular value for the Pearson's correlation coefficient, there are two aspects that should come to your mind. Aspect number one, we should look at the direction of the correlation. Is it positive? Is it negative? Aspect number two, we should look at the magnitude of the correlation. In other words, what is the strength of the correlation? Is it a strong correlation? Is it a weak correlation? So these are the two broad aspects that we have here. So first, we have the direction of the correlation. Direction could be either positive or negative. So is the direction of the correlation, is it a positive correlation? Is it a negative correlation? That is the first part. And the second is the magnitude of the correlation. How strong is it? Is it a strong correlation or is it a weak correlation? How strong is the correlation? That means if you look at the example, it is the magnitude actually. And generally, the closer the points are to each other, the stronger the correlation. If the data points are stacked very close to each other, so if whatever points we are seeing, if they are very stacked to each other, they're stacked very close to each other, it's a strong correlation. The correlation is very strong. But if the points are more spread out, if the data points are more spread out, then the correlation is weaker. So that's the way we understand the meaning of correlation, right? So if the data points are stacked very close to each other, we have a strong correlation. And if the data points are more spread out, we have a weak correlation. And now with this understanding, if you go and look at the diagram, if you look at the diagram that we have here, look at the first one. I think you will agree with me that 0.91 is a strong positive correlation. Two things. One is it is a positive direction, and second is it's a very strong relationship because you can clearly see that as x increases, y also increases. If x is more, y is also more. Okay, so as x increases, the y also increases. We are seeing a strong positive correlation. Similarly, if you look at the next example, you can see minus 0.95. We are seeing a kind of a strong negative correlation. So minus 0.95, we are seeing a strong negative correlation. So we are seeing as the x increases, the y kind of decreases. So we are seeing a strong negative correlation here. So as the x increases, the y decreases. So the correlation is negative. It's inverse, as you can see on the screen. It's inverse relationship, and it's also strong. It's strong inverse negative relationship. And if you look at the last two are great examples, which highlights the magnitude property very nicely. You can see the last two examples, which, as I said, they highlight the magnitude property very nicely. So you can see income versus spending. This is a weak positive correlation. Why is it a weak correlation? Because you can see the data points are more spread out. It's positive. Why? Because if income is more, spending is more. So that is the direct proportion we are seeing. If one is high, the other also increases. It's also high, and it's weak relationship because as x increases, there is no clear pattern for the increase in y. Y increase is more haphazard. So that's why we are seeing a weak relationship here, whereas this one is also a weak negative correlation. So this is a weak positive correlation. This is a weak negative correlation. You can see as age increases, the health quality reduces. So more the age, lower the health quality. So yes, we have a negative correlation, but we have a weak negative correlation. So what we see on the screen is a kind of a weak negative correlation. So that's the inference that we are able to make right now. So this is how we can study the relationship between different variables. I want to just add one small pointer that correlation does not imply causation. So in all these examples, we are studying two variables, bivariate analysis, two variables. We are looking at correlation. We are looking at relationship between two variables. But remember, correlation does not imply causation. So although you can say that, temperature, sales, and ice cream are correlated, so we can say that more the temperature, more the ice cream sales, which is very logical, right? So as it gets hotter, people tend to buy more ice cream, and we are getting more ice cream sales. It's logical. We can say they are correlated, they are related variables, but we cannot say one is causing the other. I know it sounds logical, but you cannot make the argument that X is actually causing Y. So just by looking at a correlation, we cannot say that because the temperature is more, the ice cream sales is more. So just by looking at a scatter plot, you cannot infer causation because, honestly, howsoever, because the other argument is also possible. You can always say that because people are buying more ice cream, they have to be manufactured, and maybe there is more population, pollution, whatever, and there is more temperature. Okay, the temperature of the earth is rising gradually because of that. Okay, so because of more consumption, right? So something like that, because remember, ice creams require refrigeration. So maybe the counter argument could be that because you're buying more ice cream, not the other way, like because there are more sales, because there are more ice cream sales happening, people are buying more ice cream. Maybe they are coming back home and they are uh, preserving the ice cream, and that means they're buying more refrigerators, and consumption is increasing and all that, right? So that is leading to a rise in temperature. So the counter arguments are also true. Maybe one of the best examples will be this one. Look at this. This is step count versus weight, right? We are again very similar kind of use case. Think of one of these smart band devices or health smart, smartwatch kind of devices that you're wearing, and they're constantly tracking your sleep pattern, your step count, and all that throughout the day. So if you, let's say, look at the relationship between step count and weight. So let's say we are looking at the relationship between the step count and the weight in any one of these devices. We will see an inverse correlation. We will see a inverse relationship between step count and weight. We'll typically see that more the step count, okay, we will typically see that more the step count, lower the weight. So that is the pattern we will make out. Okay, as the step count increases, the weight reduces. That is what is expected. Remember, it's not causation, it's a correlation. You're expecting that as people take more steps, they tend to lose weight. Those people typically have lower weight because we are expecting that as you take more steps, as you keep yourself healthy, you will not become obese, right? You will probably stay in shape and you will lose weight. But the counter argument is also true. We can always say that because you're already having a high weight, that is why you're taking less steps. Maybe because that is preventing you from taking more steps. You see what I'm coming? So you can say that because X is more, Y is less. Or you can also say because Y is more, X is less. Both are true. So if just by looking at the plot, you cannot say for sure which is causing what. So correlation is not a causation. Remember, please keep that at the back of your mind. So any use case you work in data science going forward, whatever use cases we do, we talked about that beautiful use case of network parameters versus network intrusion detection. These are all correlation use cases. It's not a causation use case. You can never say for certain that because the network parameter is this, the intrusion happened. No, we are only looking at relationship. We are only trying to associate. We are only trying to say that, okay, this and this are happening together. So next time I see a similar pattern, this I can predict. And it's all about pattern discovery, because the moment you talk about causation, you have to do a proper experiment. So data science and machine learning is all about pattern recognition and correlation, not causation. So these are two very, very different terms. Okay, causation is a proper experiment. So for example, if you want to uh, perform a causation experiment on this thing, if you want to perform a causation experiment to prove that step count indeed reduces weight, let's say Samsung Galaxy Watch wants to conduct an experiment. They want to conduct a, a social experiment saying that if you take more steps you actually lose weight. So if they want to do that, then they will have to do it in a proper experimental setup, which means taking a sample set of people, 50, 100 volunteers they will take, put them through the same facility. Maybe they will keep them in a facility for 4 to 5 months. They will monitor them. They will give them the same diet. They'll keep them the same, living conditions, and you will subject them to the same living conditions and everything. So the idea is to keep every other variable constant. So the moment you're trying to prove causation, you have to keep every other variable constant, which even like goes down to the kind of food you eat and the kind of place you live, right? So even that you have to keep constant, because if we change that, if we make that variable, then there are other factors that are coming in. So that is how a proper experiment is conducted, right? You keep every other factor constant, you modify one variable, and then you see how it changes the other variable. And in fact, that is how your clinical trials also happen. Clinical trials are the causation studies happen that way. You take a sample set, you take a and that's how you do clinical trials, right? You keep the different parameters, you monitor, you keep different parameters constant, and you see that, okay, when I administer this dose of medicine on this person, this is exactly the change that is happening. So by keeping everything else constant, you're monitoring that by giving this medicine, this is what happened, and by giving this medicine, this is what happened. That is how a lot of these weight loss medications, diabetic medications work out. So they're very, very careful clinical trials that happen. It's not like you're just based on causation, you're saying, okay, you take my drug and you will lose weight. But no, I mean, the moment you talk about some reputed body giving clearance medicines, they go through proper causation trials. Okay, but a large part of data science that we see today, and a lot of the problems and exercises that we will solve, is purely based on correlation, right? So this is a very conceptual thing, and this is what I meant. Like, as we study, you need to be very clear with how you need to study, and this is also part of what I'm trying to do. Okay, because oftentimes we just study because we have a course or we have some session where we just study, but sometimes it's very important to know how to study, right? So this is the way you should study. So try to have a very good grounding of the foundations, but you don't need to necessarily know how to do correlation, because now that you have the grounding, now that you know what is correlation, you can always go to Gemini, type some code, write a prompt, and it will generate the entire code for you. Okay, so this is useless, this you don't need to memorize, but this is important. That's the difference, right? You should know what these ideas are. So because if you know these ideas, you can always go to Gemini and you can prompt it to write this in a certain way. Okay, now let's come to the meaning and the interpretation of the graph. So what we are trying to predict is sales, right? We are trying to predict sales. Sales is the output variable. And what are the input features? We have TV, we have radio, and we have newspaper. So based on the TV, based on the radio, and based on the newspaper, we are trying to predict the sales. Okay, so I repeat again, based on the TV and radio and newspaper, we are trying to predict the sales. So that's the sales prediction we are trying to do. And when we generate the correlation matrix, this is the individual correlation values. In fact, you can actually plot the correlations also. So if I just go and take this, if I just say data.core, I will just say copy selection, maybe create a new cell. This is how you can create a new cell, and I will just paste it. So when you do this, you can actually get the entire correlation table, right? This is what data.core will do. So data is the entire table. That is the entire data frame which I had. And when I say .core, it will give me it'll basically give me the complete, uh, the complete table, which highlights all the correlations as you can see on the screen. And all that we are doing is we are wrapping it in a heat map. Okay, the heat map is just kind of wrapping the whole thing. So for example, this is the relationship between TV and sales. This is the relationship between radio and sales, 0.57. It's a moderately positive correlation. And this is a weak positive correlation, newspaper and sales, very close to zero. So this also tells you that newspaper is a bad predictor of sales. Okay, so this is also telling us that newspaper is a bad predictor of sales. If I at all have to go and do a sales prediction use case, newspaper is not the kind of feature I would like to use, because maybe that is going to add noise to your data, and sorry, to your model, and you will not end up having a very good quality model. And I'll talk more about noise and overfitting and all these things later. But just remember that the initial thing that we should do as a data scientist when you get a data set and you start working on it is to identify features which are good predictors of the output, and correlation is one of the first things that usually comes up. And there are other ways to do it. We'll look at some other methods when we talk about more advanced algorithms. What are some other methods around it? But this is the most obvious way to look at it. The most obvious way how you identify based on certain inputs which are the best predictors of the output. Okay, and you take only those inputs forward. So now going forward, you only consider those inputs to predict the outputs. You don't consider the other inputs. So the two things you achieve. One is you end up only taking important features, and second is you only you end up removing features you do not require. So you end up reducing the size of your data. So if you have, let's say, 100 input variables, all the 100 input variables are not important predictors of sales. So you don't need to consider all the 100 input variables to predict the sales, not required. So what you can rather do is you can only consider those many variables that are important predictors of sales, and you can drop the rest.